All right.
It doesn't work.
What?
Hello, everyone.
Yes,
So, two important things at the beginning tonight. So, important thing number one.
Yeah.
A week from today, I would like for all of you guys to turn in your ideas about the final project.
But then you're right.
And so it can be very short. I do not want a lot, but I want you to think a lot about it, okay? So next Tuesday, after class, you should send me a one-paragraph summary of what it is that you would like to do for your final project. And it can be as simple as, well, the input to my program is the following, the expected output of my program is the following, and the type of a method I want to implement and expand and generalize and make faster is a method based on the paper blah, 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 and my idea to make it better is the following idea. Okay, something like that. So what goes in, what comes out, should come out, and what is it that you want to implement based on what existing package and tools and software and algorithms, and how you would like to make that better. And better can mean different things, right? More general, more specialized, optimized, parallelized, applied to something different, right? It has to be something that goes beyond what is written in the latest paper about that particular type of method. And of course, by all means, I encourage you to relate your final project to your own research, then, right, you don't waste your time. Compliment. I will be very flexible with respect to the topic. So this is advanced visualization. Of course, it should be a project that relates to making pictures, right? Visualizing something. But it is, if it is more along the lines of numerical algebra and doing some computing very efficiently, very effectively, parallelizing certain things, making something very real time, right? And that it really goes into the area of numerical in algebra, fine, right? But show me that it relates somehow to allowing real-time interaction with a visualization, for example. Or I'm also open to, architecture-based, GPU-based, parallelization-based methods, okay? If there's some great algorithm out there, but no one really has figured out how to parallelize it very well with the data structures and the method, then that's cool too, okay? And of course, if it goes more in the direction of computer graphics, right, animation and making pictures of dinosaurs, whatever, right, dinosaurs with different material types and different surfaces and different subsurface scattering under the skin and all of that, fine, okay? But it has to have some kind of link back to, right, visualization. But I want to be very broad. That is number one. Number two is, those of you guys who have not signed up yet for the demo, there is still slots open, of course. And please now put a time down there for the Thursday night. We will be doing the demos also on Thursday night. And some of you already claimed Thursday, but we don't have times there yet. So again, on Thursday we should start at 7:40, and then we go until, well, 8:30 or so, okay? So if you are down there for Thursday, or you put Thursday down next to your name, put the time down for Thursday between 7:40 and 8:30, okay? Okie doke. Lecture. I should start with the lecture. Next topic is very important topic, scattered data approximation. So what is the general context? The context is that people or instruments perform measurements somewhere in an irregular way, and you would like to reconstruct the particular phenomenon or the particular geometry that has been sampled, that has been observed, that has been measured. So in the 2D case, you have an x-axis, a y-axis, and the function value, and maybe you have a bunch of observations that live at these scattered locations, so there is no structure anymore to the location of these measurements. They are really randomly located. And at those sites, so those little circle guys are called sites. Usually, you have dependent function values, and I draw them in the f direction. And of course, for rendering, when you want to make a picture, you do not just want to show these sticks, but you would like to reconstruct the smooth function between these sticks. Right? That's the whole problem of scalar data approximation. So you have the measured or scanned or observed function values at these locations. And for rendering, of course, you would like to have something like this. And you make a picture of that, the Garot shaded surface, then you would like to be able to evaluate over this respective area where you have your samples. So this location would be a location xi, yi, and you have a dependent function value there, fi. So what's given? Given is just this set, finite set of sample data, xi, yi, and the dependent function value, fi, and you have n of these guys. And what is wanted? Wanted is this guy, this function f of xy, which I represent by this curved creature. So wanted is a function f that should initially only satisfy one condition, namely that when I evaluate this function f, it should reproduce the measurements fi at the sites xi, yi. Function f such that st such that f, when evaluated at the site, reproduces that value that I'm given there. That's all. And I think I will just walk us through the methods by starting with a very simple one-dimensional, right, curve example first, and then from the curve we can go to the surface example, and then once we understand the surface, then we really know how to do that for the volume data, right? Yeah, visualization, volume visualization, we really want to apply all this stuff really for volume data, right? Temperature field in this room, right? You want to do a volume rendering of the temperature in this room, but you only have 10 thermometers in this room, right? So 10 readings, that's not good enough, so you want to reconstruct the entire continuum, and you do that by, well, applying something like that. But this something has to be a good something, so that's why I talk about it. So we start with the 1D / univariate case. Okay. All right. In the univariate case, what does the situation look like? There we only have one dimension for the location of the sites and one direction for f. And we have these sticks, which are now randomly spaced. And I call these locations x1, xi, and the last one is xn. All right, so what is the problem? The problem is I would like to draw some kind of smooth curve or high-resolution polyline, right, connecting these sticks. What's the general approach? The general problem is I need to evaluate this continuum function that I no longer have or that I never had at this arbitrary value x. Okay, so when I need to evaluate at this location x, then I should combine all the measurements in some way. And the general principle is a principle that's very simple. Data that is very close to me should have high or low importance when I evaluate here. Data that is close to me should have high weight or low weight. High weight. And data that is very far away from me should have low weight, okay? So the weight, how to combine these observations, should be related to how close or how far the samples are away from me, me being at the location, I standing at the location where I need to estimate the value, right? So that's the whole principle. So being close, being far away relates to what measure? Distance, right? So if something is close to me, it should have high weight. So small distance equals high weight. Something is far away from me, high distance value should have low weight, right? So that's the principle. So therefore, I should combine all the given measurements in such a way that I use distance in a reciprocal way. Huh? All right. So general principle. data close to x should have high weight when estimating a value. Making a function value, fct value, f for location x, for location slash site x. So this general principle then translates into a simple formula, and this formula obviously has to include distance. And this was done by this, I think, high school student at the time, or undergraduate student who invented that. I think high school-aged student who already was pursuing graduate studies at the age of 16 in geology. And so this is called Shepard's method. You can look him up. Shepard's method. And there will be a variety of them, and I call the first one S1. So if there is a Shepard method S1, there will be an S2, and an S3, and S4, and so forth. S2, S1 of x, will do the following. Whenever I evaluate this Shepard function at one of the given sites, then I should reproduce the values there, right? At the sites, at the circles, I should be able to get the bullets back. Okay, so that's the first condition I write down. It should reproduce fi if x is one of the sites, if x is one of the xi's. And otherwise, it should be a combination of all the values in such a way that those close to me have high weight and those far away from me have low weight, using the distance at the immediate weight. When I actually write this down, what this means, it means that I combine, combining is summing up from 1 to n. I combine all the observations fi, and I use weights that are the inverses of distances, 1 over di, divided by the sum of all the weights, 1 of di. Otherwise, now I just need to say what the di is. The di is the distance function, the distance of a site to a particular evaluation location, where the distance di is di of x, and so distance is square root of x minus xi squared. Okay. What type of a function do you get? Will the function that you get when you program this look good, or will it look bad? I already said there's an S1, there's an S2, there's an S3, there's an S15. So S1 is probably pretty bad. Okay. Otherwise, there would only be an S. All right, so, okay, it will interpolate here, but otherwise it looks pretty ugly. It could look like that. Okay, it does the job, namely going through the points, but that's about it. The way I've drawn it, you see that there are slope discontinuities. It is not smooth, right? So it is just what is said to be C0 continuous. But the resulting function S1 has slope discontinuities, gradient discontinuities later on. Slope discontinuities, at the xi sites. So this is bad. There's a simple fix to that. we use the square of the distance, di squared of x, instead of di. So you get a new Shepard, Shepard 2 equals. All right, so at least I should tell you how you actually prove this, right? The general idea. How do you prove that indeed this thing has different slopes when you approach the side xi from the left and from the right? How do you prove that? That the slope really disagrees, approaching this particular location from two different sides? You do the limit, right? Huh? You actually evaluate this formula for xi minus an epsilon, and then let epsilon go to 0, right? And you approach xi from xi plus epsilon, let epsilon go to 0, and then you will see that you get two different slopes. Boom. So same with here. Here I will claim that this thing is slope continuous. Again, how do you prove that? Again, by making sure that in the limit process that the slopes agree at the sides. And that's how you will see it in the papers. So S2 looks just the same, except that we say interpolate the given datum fi if I am at a location xi, or otherwise combining means computing a sum of all the values fi weighted inversely proportional to the square of the distances 1 over di squared divided by the sum of all these weights 1 over di squared. Otherwise, okay, so di, where di squared is what? Well, it's just the square of that, so the square root goes away. Where di squared of x is just x minus xi squared. Okay, now you get a better function. What do I mean by better? Well, at least the slopes are continuous at the sides. But it will look like this. And you tell me whether that is cool or not. Okay. These are the sides. Circle, 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 circle. These are the values. And since I have computed these things, right, for many decades, I know how they look like, and they always have a 0 slope, okay, at the sides. Meaning, whenever you evaluate this function S2 of x at any of the sides xi, and you differentiate that, then you always get the slope of 0. Is this nice or not? You have plateaus everywhere, right? So the function actually will look even worse. It will look like this. Okay, that's roughly the nature of the beast. Is this nice? It solves the problem. Maybe it's nicer than this. Probably is, in some sense. But still we don't like this fact that whenever I'm at one of the sticks, I have a 0 derivative. Why should I? Right, my IC is a much smoother curve going through there. All right, if there is S2, there is also, sir? Tell me your name.
There's an S3 too, I guess. Before we move on, though, can you put what the actual limits on the sum are in the denominator? Or which one? I can't remember which one is which.
I have from 1 to n.
So, because I can't really tell what the difference is between the sum on the top and the sum on the bottom.
On the top, I multiply all the given function values by this distance expression.
By their fi. Okay, yeah. I got you.
Okay, the distance expression is a weight for the function value. Okay, I come back to the meaning of such formulas. They are convex combinations, etc., etc. So we have these flat spots or plateaus, and they are not nice. Huh? So we have these undesirable flat spots or plateaus. Okay. Now, how can I fix that? This is all I have. I have 5 sides and that's it. I don't have anything more. I have 5 sides and 5 sticks. And my method is always taking the stuff that I have, namely these data, the dependent data, and combining them in this way. We already talked about in the first assignment, right? Besides just prescribing the value, the given value, we can also prescribe what? This one should look like this, right? This one should look like this, and this one should look like that. And here we should have a slope like that. Okay.
The gradient.
Okay, so we have an oracle here, right? Oracle is a modern term, right? People like to use that, I guess. So we have a method here that has some data which are being combined. Instead of just combining function values, we can combine function values plus slopes. You blend things, right? You are averaging things. All right, so instead of just prescribing the function value, we now will prescribe a line at each side. The line is not given to us, right, in the beginning. In the beginning, we are only given the function value, so we need to worry about, again, computing the estimates, right, for those lines. But assume that we have these good estimates, then we want to interpolate to those first-degree approximations. So at each side, we now actually have a line. We will be averaging or blending lines together to get a better look. S3 of x besides fi values, assume that good slopes fi prime values are also known, semicolon, and then we will just combine line equations or lines from each side. Then generalize method to combine line equations or first-degree Taylor approximation that decides to combine line equations. Associated with the sides. Okay, so the picture now looks as follows. We have our line, we have our function direction f, x, our sides, something like that. And we assume that we also have meaningful derivatives at these locations. And our eye is always a good judge to see what good derivatives are. Right? At the beginning, it should start like this. Here, it should look like this. Here, it should look like this. Here, it should look like that. And here, it should look like that. Right? Somewhat like that. And the resulting function we would like to get should look like this. It should interpolate the function value as well as the slopes. Okay. So it's better. All right, so this is an xi. This is the function value fi. And this guy would be the derivative fi prime. Okay, so the formula now will blend line equations. Right? Now we have a little Taylor approximation of the function at every side, and we will blend or combine, average all these line equations together. And so the formula S3 of x looks as follows. We have to understand what a single datum now is. A datum is now the definition of the line. So we have an fi. It's no longer just an fi, but it's a line equation, so it's an fi of x. And fi of x is the value there, the function value fi, plus the derivative there, fi prime, times x minus xi. Right, that's the line equation passing through that value fi, having slope fi prime. When you differentiate this guy with respect to x, well, the differential is fi prime. And the shift is x minus xi, so it's actually 10 of that. All right, so again, it is fi if x is an xi side, or otherwise it will be a combination, sum from 1 to n, 1 over di squared, times, now these are fi depending on x, these are the line equations, fi of x divided by the sum of all weights, 1 over di squared, I from 1 to n. And the important part is that this is now functions that we are actually blending together, not just function values. All right, now that we have that, we have to talk about getting these derivatives, right? For the first assignment, it was easy because the first assignment was just working on Cartesian grids, right? Everything is just always 1/2 right minus left. In all the papers, it's always 1/2 right minus left. That's the differential, right? It only works for Cartesian measures. So we have to do this for this setting. And if we understand it for the 1D case, then, well, usually one can also understand it easily for the 2D case and 3D case. Let's do that. So this is just a little note. Since the derivatives, the slopes at the sides are not given to us, we need to compute them fast and in a meaningful way. So this is just note or remark. Note, we need to compute good fi prime values at the sides. Computation of good fi prime, i.e. slope values. How do we do that? Okay. How do we get good slopes? At this point here, what kind of slope do we want? Do we want this zero slope? No? Do we want this slope? What slope do you want here? This one? Tell me when the slope is good. No good slopes? Not at all? Your eye tells you what a good slope is, right? So we only want to understand what one can do if one has just the local neighborhood to consider, okay? So this is a very simple way of looking at it. So here is the side xi. Here is xi plus 1. Here is an xi minus 1. Here are the values that we are given, and only that. And we want to get a slope there. How do we get a good slope there? Is this a good slope? No? Is this this slope is better, right? It's this slope? Right? No? Okay. So this is a meaningful slope, that's a meaningful slope, but either one isn't really good. This would be better. So it's somehow related to the slope coming from the left and the slope coming to the right, if you just consider this particular slope. What about this? I can also do this, right? And differentiate that parabola. Okay. Or what about this? You can do that too, right? So there's different ways to think about that. I will just talk about one. But I want to tell you that there are many ways of getting good slopes. So take this in, okay? This is a center point, and of course it has a left neighbor and a right neighbor. So the slope here in the middle should be an average between this one, the line from the left, and the line from the right. You can combine these in some way. Should it be 1/2 of that slope plus 1/2 of that slope? Not really, because we don't really have the delta, right? The same spacing here. There's an arbitrary spacing now. But you can think of it that way. Well, there's some line like this connecting this. And there's another line there. And somehow you can combine these two slopes in such a way that a good slope estimate in the middle comes out. That's one way of thinking about it. The other way to think about it is you have a quadratic polynomial, a parabola, that goes through 3 points, right? A parabola is always a plus bx plus cx squared, right? You can do that. 3 values, 1 parabola. Or then there's something that I will talk about because it's, in a sense, the cheapest. You compute what is called a least squares line. There's a line that is the best possible approximation to 3 values. So there's one unique line that is the best I can construct, getting close to these 3 data. Never really interpolating them, but getting very close to them, as close as possible. And then I can look at the slope of this line and say, that slope of that line is the slope that I use for that point in the middle. Okay? So there are many ways, many possibilities. And I just give you one. One is construction of the least squares line. Determine the best possible line L. This is that line. Best possible line L, approximating the 3 function values with minimal error. Approximating the 3 function values, 3 FCT values, fi minus 1, fi plus 1, with minimal error. So with minimal error, that includes something is really best here, right? It's minimal error. Okay, continue that here. Illustration. Xi minus 1, xi plus 1, fi minus 1, fi plus 1. And you believe me that there is one best line that is as close as possible to all 3 data, right? And your eye sees that line. The line is this one. It's unique. There's only one line that minimizes these 3 differences. Okay. So L is a line, depends on x. And a line is defined by 2 points, right? So here we have 3 data, therefore it can only approximate, and we want to get the best line. So we write down the conditions anyway, the conditions to interpolate the 3, which it cannot really do, and then we minimize the errors. Okay. 3 interpolation conditions. Interpolation conditions for the line L of x, which is of the form, say, a plus b times x. Right? 3 conditions. Conditions are, I can write this down as a matrix. My unknowns are the coefficients a and b, and they should the line should interpolate 3 values, which it cannot, but it should interpolate fi minus 1 and fi and fi plus 1. Since it cannot interpolate, it should approximate as best as possible these 3 values. And so now I plug the different sides into that equation for x. So it is 1 times a plus xi minus 1 times b equals fi minus 1. Then I have a plus b times xi equals fi. And then I have the last equation, 1 times a plus xi plus 1 times b equals fi plus 1. So this is an overdetermined system. I have 3 equations for only 2 unknowns. So this is some kind of matrix M times a coefficient vector a equals some vector of function values f, right? That is the system you have to solve, and it's overdetermined. So, and now you do what is called the least square step. You solve the corresponding least square system. Solve least squares problem. And after many, many transformations, I tell you where this comes from. We actually just solve M transpose, MT times M times A equals M transpose times F. And so this little T symbol is just the transpose of this matrix, right? Flipping rows and columns. T means the transpose. Okay. How do we get this? We actually write down the expression for the differences between the actual value on the line and the value at those sites. And you express these errors, the sum of these errors squared, as a function of the unknowns a and b. Then you have a function in 2 variables a and b, and you would like that function, the error function, summing up the squares of these differences, to be minimal. So then you have that function. In order for a function to be minimal, you have to differentiate it with respect to its a and b direction, and you have that necessary condition for the gradient there to be 0, and ultimately you end up with this equation that solves it. Okay? So this comes from normal equations. Normal equations. But this is very fast. So here now we have, this is a 3 by 2, so this is a 2 by 3. Ultimately, when you multiply them, it's a 2 by 2 matrix, right? 2 by 2 matrix times the 2 unknowns equals a vector of 2, right? Entry isn't right inside, so it's a 2 by 2 problem, no big deal. The only expensive part is to multiply the 3 by 2 matrix with a 2 by 3, that's it. But that's not expensive either. And you get ultimately the slope. So therefore, what do you get out of it? This guy has a particular slope there, right? This is what I will use as the derivative at this side, right? And that is just this line equation differentiated at xi. But, well, this line has the same slope everywhere, so it's just this coefficient b, right? The only thing that I'm after is b. I only have to solve this thing really for b. I only want the slope, just the slope. I just want that b, the slope of that line. So this is B. L prime at xi is B, because the slope of the entire line is B everywhere. Right? Okay. And this is the end of the remark, or the end of the note. Does it all make sense so far? Make sense? Okay. All right. Now we understand everything for the 1D case. Then we can go to the 2D case, and we can go to the 3D case. One question, in the meantime, I want to throw in there. Is this whole method of averaging all these function values efficient and fast or not? What is the expensive part in doing all of this? Huh? This one. Here we have it. What is the expensive part to compute this value, S3? The expensive part is the sum. Is the sum a small sum or is it a big sum? I have 10 temperature readings in this room. It's a small sum. Okay? But I have, say, a terrain, a height field, measured with laser scans. Lasers can produce a lot of samples in a matter of a femtosecond, right? So this n can be very big. When this n is, say, above 1 million, then even the latest GPUs get slowed down. Okay, so this is expensive. So that's just want to mention that. Okay, so therefore these methods are also called global. They consider everything. For example, if I want to reconstruct the temperature field, right, in this layer that is 1 kilometer up from the ground to 1 kilometer up, and I have temperature readings all over the world, and I have 10 billion of those temperature readings, and I want to reconstruct using this global n all 10 million readings or whatever, then it's expensive, right? So you want to, well, does the temperature reading in Europe actually have an influence on the temperature reading here? Probably not. Okay, so therefore, do you always have to use all 10 million? No. The trick is how to use a good n, right, a local n. All right, so that was that. So now we talked about the 1D case. After the 1D comes the 2D, right? 2D or the bivariate case. Bivariate case. What changes? Nothing. Nothing changes. I don't even need to put anything on the board, right? Or should I? I should, right? But nothing much changes, except that the definition of a site changes. A site is no longer just an x, but it's an xy. It's an x1, x2. Huh? Two variables. Does it change when we go from 2D to 3D? No, except that a site is no longer just an x, but it's an xyz. But the whole apparatus, the whole way to average and combine the values, the temperature readings in this room is the same. Mm-hmm. All right, nevertheless, let's do it. So a simple illustration in 2D, I would have some readings in the plane. Can think of these as maybe height values, terrain data, scanned with the laser scanner, giving you several millions and millions of points. So again, the interesting part is that these locations are random. Randomly located. And I have my xi, yi, and I have an fi. And again, what I want is for evaluation or for rendering purposes, I would like to have a nice, beautiful shaded surface there, happily Gauss shaded with little quadrilaterals, and applying a lighting model, not just showing the sticks. So, given is now the set of xi, yi, fi, I from 1 to n. And wanted, well, the wanted was already on the board. I had this already, right? That was at the beginning. I motivated the whole thing with this particular picture anyway. So this picture is kind of like at the center of everything. The 2D setting is a little bit more complicated, a little bit more difficult, right? From the 1D case, Why is it? It's the arrangements of the points, the arrangements of the sides. Right? Here in the 1D case, at least you have this notion of when I'm here, this guy has a left neighbor and this guy has a right neighbor, right? This is lost now. You see that? Nothing is that easy anymore. So it's becoming a little bit more general, more complicated, right? Random sides on the line, yes, but still there's an order, a natural order, right? The smallest side value, x1, it's indexed in such a way that x1 is the smallest x, that xn is the largest of all x's. Huh? So there's a natural order in there, from left to right, from smallest to largest. You cannot do that here, right? Which point is the smallest? There is no inherent ordering from this is point 1, this is point n. Point 1 is the one that is measured first, and point n is the one that's measured last. Huh? I could also measure these guys coming from the right and going down. I could say this is x1 and this is xn. But you see that it makes it more problematic. Okay, so let's just write down what S2 is. For example, what is S2 in this case? For example, S2 in this case looks like what? Shepard 2. It is now a function depending on x and y, which is what, again? It should reproduce the fi value if a tuple xy is one of the sides xi, yi, and otherwise it's a combination of all the sticks, all the data that I'm given. Otherwise it's a combination sum I from 1 to n dividing by all the distances I from 1 to n. The weights are 1 over distances di squared times just the function values for S2 divided by the sum of all weights di squared. Okay. Otherwise, okay, what do I have to say? I have to say what the di squared values are. Where in this case, where now di squared is now di squared of x and y, which is x minus xi squared plus y minus yi squared. Otherwise, everything is the same, except that now the number of variables grows and grows and grows and grows. That's it. S2 is already smooth. Okay, but what will it look like? What did S2 look like in the 1D case? Don't copy this. This is just kind of right in our memory bank. We are remembering what S2 looked like in 1D. It looked like this. It had these plateaus all over the place, right? So if in 1D it produces these types of plateaus, what will it do in this case, in the 2D setting? It will produce happy plateau regions at all the sites. So it will look like the, in a sense, like Monument Valley. Monument Valley, you have also the rocks, and they're flat, right? It will look like that. Right? There's these little rocks coming out with the function values, and then it's flat. And the immediate neighborhood has the same value. We don't like that. Shoot.
I have a question about the sub-value I. Should it be I comma j since we're doing x, y?
No.
It's I?
We are just still calling the first one, point 1, and the last one, xn, yn. We just use one index. These are just the independent creatures, right? First point, second point, third point, nth point. Okay? It's the number of dimensions, x, y, that has gone up. But in terms of indexing or numbering the elements, they are still from 1 to n. All right, so there are plateaus. We don't like that. How did we cure that in the 1D case? What did we do? We prescribed slopes. And in the 2D case, what do we prescribe? Tangent planes. Planes, right? Osculating planes, touching planes, gradients, gradient behavior, slope behavior in x direction and y direction, right? All right. So this one will have plateaus And we don't like that, so therefore one has to worry about an S3 which considers entire linear functionals being interpolated. Linear Taylor expansions. But S2 of xy has flat spots which are undesirable unless you do an animation that should look like Monument Valley and you want flat spots, right? Which are undesirable. Therefore, use S3. Okay, all right. So for S3, as I said, now we need something in addition to the original 6. So these are our locations. And our height values, or function values. And this doesn't suffice, but we also prescribe the derivative behavior there with a plane. Just have a little plane there that you can tilt around and change its normal. And well, there is maybe a best one, or a good one. Not a best one, a good one. So we prescribe a little happy tangent plane here, which has a particular slope in x and in y. And again, we will need to talk about the trick how to get a good one. So we have first degree Taylor expansion at this particular site. The site here is xi, yi. So then this guy is function value fi. And I have two gradient components, the derivative fix and fiy. A local linear polynomial is again an L for linear, L of xy. Well, this plane or this linear polynomial lives everywhere, right? And we'll blend them all together, right? These little tangent planes define a linear polynomial for all the sticks, and ultimately I will merge them, combine them, weight them, average them, and then Li of xy will be, well, fi plus fix times x minus xi plus the gradient or the derivative in bidirection at side I, y minus yi. So this is times. Okay? So this means that the gradient grad of Li is indeed fx at location I and fy at location I. When you differentiate this expression with respect to x, then you get this value. When you differentiate this expression with respect to y, you get that factor. And those are the two components of the gradient of that function. Okay. So now we assume that we have these happy linear polynomials, these happy planes at all sides. Now we can talk about S3, and I can write it down. And then we have to talk about how to compute the polynomials, right? Because that is a little bit more complicated than the 1D case. Okay. Therefore, we now have our S3 for the bivariate setting to approximate something over the plane. And S3 will reproduce a measurement, Fi, if the side location, the tuple, is one of the sides, xi, yi, or otherwise it will blend something. Blending is summing up or integrating. And it sums what? It sums linear polynomials. It is summing linear polynomials Li of xy's, which are weighted by the distances squared, di squared, over all n, from I from 1 to n, I from 1 to n, 1 over di squared. Otherwise. This is, in a sense, just a combination or a blending of linear Taylor expansions at all the sides of linear Taylor expansions. Known at all sides. At all sides. That's one way of thinking about it. Okay, but I didn't really say how we get these happy planes, right? How do we get a good plane? How did we do it in 1D and how can we do it in 2D? All right. So now you need to help me, okay? Be creative and tell me how you would tackle that. Don't copy this. This is just to remember. In 1D, I said, well, Bernd, you have 3 sticks, and I want to use as a slope here the slope that is the slope of the best possible line approximating these 3 data, right? So the best line here might be this one, so I copy that slope over to use it as a slope for that middle point. But again, this whole thinking is based on the notion of central point. Central point is the left and the right neighbor, right? Here in this setting, there's no such thing as a left neighbor, a right neighbor, a front neighbor, a back neighbor. There's no mesh, there's no grid, there's no order. Something is point 1, this is point 1, this is point 2, this is point 3, this is point 4. It's random, it's scattered. How can we still do something like that? Pause. 1 minute thinking break. Dun, dun, dun. Okay. If I just wanted a line equation, a plane equation, how many data do I need to define a plane in 3-dimensional space, a linear polynomial? 3, right? 3 would be good enough. So therefore, I could say, if I'm at a particular site, use that site plus 2 others to define a triangle in space, and the triangle has obviously a slope because it's a plane equation, right? A triangle is a plane. You can do that. Is that good enough? Should I use 3 points? Should I use 10 points? Jennifer?
Probably depends on which other points you're picking.
Which points do I pick?
The closest one.
I should pick closest ones. Close ones is good. But how many? How many of those closest ones should I pick? Just 3? 50? Until using more, it doesn't make a difference anymore, right? So in the 1D case, I use just 3, right? 3 points, 3 sticks to get a good line. I could also use 5, right, to get a good line. There's no restriction on that. At some point, it doesn't make a difference anymore. And at some point, the sticks are too far away, and I should not consider them because they are far away, right? So this is a trade-off. You want to have a local scheme which only considers local stuff because the stuff far away should not have an influence. Versus, well, if I just stay too narrowly, right, focused, that is maybe not good either because I should see a little bit further than just beyond this room. I should see 1 room, 2 rooms, something, right? So it's an experimental parameter. There's no good answer for that. Therefore, people use K and N. K and N stands for?
K nearest neighbors.
K nearest neighbors. Right? So they use K nearest neighbor graphs, wherever these complicated terms are. So, so this is now how to estimate. Right? This is just an estimation. Estimate it's really estimating gradients, right? Gradients. And the gradients are these little vectors, the fxi, fyi, for the sides, xi, yi. Right? So the index I appears up here in the superscript. That shouldn't disturb you because I use the lower subscript as to indicate differentiation with respect to x and with respect to y. Okay. All right. So how can we do that? Okay. So here's my site for which I need an estimate. And I consider, say, k equals 6 for whatever. 6 is a good number, right? You like the number 6? I like the number 6. I think it's a very good number. So there's a site in the middle, and it's surrounded by, well, there are 5 of all the other points, which are the 5 closest ones. Hopefully they are distributed like that. There's no guarantee. The 5 closest ones could all be lying on a line to one side, okay? That's ugly too. So anyway, so we have these are the 5 closest ones. I just indicate that. There's no real connectivity. Again, there's no mesh, there's no grid, right? These are use the big guy plus 5, which is plus 5 nearest neighbors. Nearest neighbors. Okay, so this is a 5nn, 6nn if you count the big guy in the middle as well, right? Plus 5, the smaller guys, in its neighborhood. So here we have the sticks, we have the function values here, and they're probably in the analog way to the 1D case, there is probably a plane, right? There's probably a plane that is the best possible plane that I can place there that has minimal distance to all these sticks. There's no plane that passes through all these points. 6 points not possible because 3 points determine uniquely a plane, right? But there's one plane that is the best plane. And I want to get that best plane and then use its slope behavior in x and y to specify the slope at this guy, at this location, right? That's where I need the slope. That's what I want. So I do a local indexing, and I call the guy in the middle function value 1. I call the guy here f2, f3, f4. This is just a local numbering. These are 6 selected ones from the entire set of given data. And they are just a subset in this local neighborhood. So this is function value 6. And now this particular linear polynomial has a certain form, Li of xy. If it's linear, well, it will have the following form. It is just an a plus a b times x plus a c times y. That's all there is to a linear polynomial, right, in 2 variables. Okay, and now I would like this linear polynomial to approximate these 6 sticks, and I write this down. Here, 6 equations. Okay, and again, I always like to write things down in matrix notation. So there is some kind of matrix. And the unknown vector is a coefficient vector, the unknown ABC vector, ABC, times, on the right-hand side, I want to approximate, ideally interpolate, but not quite, the sticks. And locally I have 6 of those, F1 up to F6. And now I just plug the different locations. This, for example, would be location x1, y1. I plug all the locations, the site information, into this expression and want to approximate an f value. So the first one would be 1 times a plus x1 times b plus y1 times c equals f1. And then I have 6 of those equations. The last equation is 1 times a plus x6 times b plus y6 times c equals f6. Again, this is overdetermined. I have only 3 unknowns, a, b, c, and I have 6 equations, so I have to use this least squares trick. So this is a matrix M times, call this the A vector again of unknowns, equals F. That's the overdetermined system, and you solve it with the least squares step. Solve least squares step, and you will solve M transpose times M times unknown coefficient vector ABC equals M transpose times the function value vector. This is still not too bad, because when you multiply this out, you just have a 3x3 system, okay? A 3x3 matrix to invert. Not a big deal. And this makes us very happy. All right. So again, this was just a note or remark. How do we get good tangent planes? All right. What should I talk about? I think I should go to the 3D case right away. And I should talk a little bit about the efficiency of all of this, right? uh, 3D case. That's the case that really interests us, 3D or trivariate case. So in that case, I can no longer draw pictures of it, except the pictures of the domain. So in this case, our domain is already XYZ space, XYZ, and the function direction comes out of the board and goes in some direction. And my data live in some kind of bounding cube, say. And we have our sites happily living in this box. Temperature readings, salinity readings, pollution readings, whatever it might be. So here we have given a set of tuples xi, yi, zi, and again it's just one index, right? All these points are just numbered from 1 to n, even though they live in 3D space, x, y, z, and a dependent f value, and we have again n of those, I from 1 to n. And so, without any further ado, we can directly write down what S2 is. S2 is Shepard 2, depending now on 3 variables, spatial variables, x, y, z. And again, what do we have at one of those tuples? At one of these tuples we have, well, this is just a location. We have the dependent function value there, an fi value, and we want to reproduce it when we evaluate at that site. It is fi if x, y, z coincides with one of the original sites, xi, yi, zi, and otherwise it should be a combination, a mixture of all those readings or observations and that is again the same. We mix all I from 1 to n. We mix them using weights, which are the distances squared. Sum of all the distances squared, reciprocal I 1 to n, 1 over di squared. And we mix the function values. And what is the distance? Where the distance I squared is now x minus xi squared plus y minus yi squared plus z minus zi squared. If there's an S2, there's also an S3, right? Should I talk about it? No, because at this point, I have to trust that you can do that yourselves. I will not talk about it. I will stay away from that. But we can reflect on it jointly, right? In the three-dimensional case, you also will have plateau regions. If this S2 thing is producing plateaus for a volumetric data set, they would manifest themselves as what type of features in a volume rendering? Okay, what is this? This is a subset of the skull of a skull data set, right? You just take a big skull data set, 256 by 256 by 256, and you just select 1,000 points randomly, right? Just take 1,000 points randomly from your originally nice Cartesian grid, and then you have a random point set, a scattered data point set. And then, if you apply S2 to it, I tell you S2 produces flat spots. So when you do a volume rendering, then you would see a flat spot around each side. In a volume rendering, how should that manifest itself? You should see blobs of nearly constant color, right? Right? Flat spots are zero gradient, right? So there's hardly any changing color, probably, right? Okay. So the sites where you are sampling, or where you have observations, would stand out as little blobs, as little plateaus. I mean, four-dimensional plateau, but you would see them. You don't like it. Therefore, you need to do S3. S3 of x, y, z is bam, 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 and bam, bam, bam. I don't need to put this on the board, right? You know the formula. It's only now the additional variable is the z, right? The z variable that comes into play. That's all. But you need, what do you need to worry about in order to play the S3 game? You need derivatives. You need gradients, right? But again, I don't have to tell you that because the setting in 3D is analogous to the setting here, right? You just find 6 points, 5 points around a point in the middle. You set up a linear polynomial. Now it will be an a plus bx plus cy plus bz. And you do the same machinery, right? Same thing. So I trust that you see that. Need to compute least squares linear polynomials, and they will be of the form for each side I. You have a linear polynomial L, which will be of the form a constant plus a b times first variable plus a c times second variable plus a d times third variable. Okay. And for there, again, you will have, in symbolic form, you will have 1, 2, 3, 4, 1, 2, 3, 4 times the unknown coefficient vector a, b, c, d to approximate all the values that you have in the local neighborhood. That will be the initial setup of your system, and then you do the least square step. Use the transpose of that matrix and solve it, just like on the other side. Okay? Bum, bum, bum. All right, now the real beauty is, if I can do this for x and y, for x, y, and z, then I can also do it for many, many more variables, right? Particularly, which is the next meaningful variable in scientific visualization? X, y, z, and time, right? So you can also do this for time-dependent fields, right? Which is the next generalization. Okay. Okay. Should just talk about, or let's think about the issue of time. Are these methods expensive or are they cheap? What is a particular setting? I would like to use this in the setting of, for example, having real-time readings of the temperature in Lake Tahoe, right? Sensors are getting very small and very cheap, so I can easily throw 10,000, 100,000 sensors into a lake. Huh? Anywhere, I can throw all these cheap sensors anywhere, they record something, right? And I want to make a volume rendering, a cool picture of this actually time-dependent phenomenon, right? Temperature in the Lake Tahoe changing over time. If I use this machinery straightforward, and I have 1 million readings, and I want to produce a nice real-time rendering, a real-time rendering would produce at least 24 frames for left eye and 24 frames for right eye, right, to do it in stereo and see it in real time. And the sensors can produce that. So can I reconstruct so quickly with this? Probably not. Because you as a scientist in the field only have a little laptop, right? Maybe with one cool GPU in there, that's it. So you have to speed this up. How can you speed this up? Tell me your name again.
William. I'm having trouble remembering this, but is that equation over there, can you use convolution to speed that up?
No.
Okay.
No.
All right, it reminded me of something we used convolution to speed up in the past, so I thought I would ask then.
No. But this goes in another direction. Convolution, and where do I need more samples, and where can I use sparser and higher resolution? If the lake temperature is nearly constant in a certain area, I don't need so many sensors, and I don't need so many readings. It's another way to kind of like keep this n down. It has to do with this n. I want to keep the n down, right? This big sum that I have to compute, these distances there, these x minus xi squared, and the squaring operation, the multiplication and divisions are expensive. That's the stuff that's expensive. No, I cannot do anything with convolutions or transforms or Fourier stuff or Laplace stuff here directly. No, I don't see that. We have to keep n down. Okay. So again, if I'm standing here in this corner and I want to approximate the temperature field here, say in a box that is 2 by 2 by 2 meters around me, then do I need to consider the temperature readings back there in the corner? Maybe I should, but I don't want to because it's too expensive. Right? So therefore, I will only consider the temperature readings in this 2 by 2 by 2 meter box around me. Okay? But then when I move, and I move here, then I have to use a 2 by 2 by 2 meter cubed box around me here to do reconstruction in this particular box, right? So that is one way to make it more efficient. Whenever you are evaluating your domain, your volumetric domain, you only consider the sites or the original data that are in that box where you are evaluating to produce an estimate. When this box where you evaluate moves around, you consider always changing data sites and data values, right? The question is, what is the speed up? Into how many smaller boxes do you have to divide this room? 8 boxes? 64 boxes? 256 boxes? At what point shouldn't you be using smaller boxes anymore because it becomes too local, the approximation, and deteriorates, right? Probably should not be used. The boxes shouldn't be too small because then the quality of the reconstruction isn't good enough. So there's a trade-off between the speed and the quality of reconstruction. What are the best numbers? The best numbers depend on the particular phenomenon and various other parameters that I didn't even talk about. But again, the important thing is that you would like to use this in a real-time setting. Right? The real-time setting is someone has a very cheap, huge sensor network deployed out there and needs to be able to produce these types of the images resulting from S3 of X, Y, Z in real time, in stereo, with 30 frames per eye, okay? On a very low-end, cheap laptop that you actually can carry with you in the field. You see that relationship there too, why it has to be portable. So, and again, this is for your next assignment, how to speed these things up and still get a good picture at very, very good speed. Many things are, of course, trivially parallelizable, right? Once you know how you can cut this room into octants, when the computations are the same in each octant, right? You can trivially parallelize it. So, okie doke. Everyone signed up for Project 1 demos? Anyone still needs to sign up? Okay. All right. So we have demos tonight, and we have demos Thursday night. And then after Thursday night's demos, we will see where we are. Okay? All right. Thank you. Everyone stay in this room. We will have demos here, okay? And everyone is invited to stay.